From the Department of Chemical and Biomolecular Engineering at Berkeley, please join me in welcoming the CEO of Joint Energy Institute, Professor J. Keasling.
Thank you very much. It's really a pleasure to be here, and I'd like to thank the government for this award. In the next few minutes, I'm going to talk to you about engineering microbes for production of chemicals and fuels in particular. So I don't have to tell the folks in this audience that all of our transportation fuels and most of the chemicals and even some of the drugs we use come from petroleum that's refined. We'd like to have a renewable future, and that would involve obtaining those fuels and chemicals from renewable biomass. If you produced fuels from renewable biomass, when those fuels are burned in the car, that would return the carbon to the atmosphere, and we have the opportunity of having fuels that are carbon neutral. Now, I'm going to talk to you today about engineering microbes to produce those fuels, because that's the central part of that biorefinery that converts the sugars into fuels that we can burn in our automobiles. Now, when we started this work in my laboratory, the only fuels that were available are those that come naturally from microbes, things like ethanol and methanol. And while those are fine additives to things like gasoline, they can only be used in small percentages in most automobiles, and they can't be used as substitutes for diesel or for jet fuel. What's more, ethanol is produced in small quantities by microbes like yeast, and the yeast die once they produce it. So you have a lot of water in there that you have to get out before you can use it as a fuel. We use distillation to do that, and that's an energy-intensive and expensive process. Once you get that ethanol, you can't pipe it through traditional petroleum pipelines because it's corrosive. I like to say that ethanol is better for drinking than for driving. So if you're not going to use ethanol as a fuel, maybe you'd like to produce hydrocarbon fuels that are identical to those that we get from petroleum. And that's been the focus of my research for the last decade. We're trying to produce a variety of fuels from sugars, fuels that behave identically to gasoline, diesel, and jet fuel. And I'm going to give you some of the details of how we do this, but I'll gloss over a lot of the chemistry that we work on. We've worked on producing long-chain hydrocarbons that are constituents of diesel and jet fuel. These are traditionally gotten from oilseed plants, but these plants are not very productive per acre. Palm oil, on the other hand, is very productive per acre, but there are a lot of rainforests being burned down to plant palm. We wanted to be able to produce fuels directly from sugars using a microbe. And so we engineered the chemistry inside the microbe to do that. We take fatty acids that are normally used to make the cell membrane around microbes, and we divert the chemistry so that we can produce things like fatty acid ethyl esters. These have the very nice property that when the microbe makes them, they actually secrete them into the medium, and it's more like making a vinaigrette than a mixed drink. And by that I mean that the oil phase, the fuel phase separates from the aqueous phase, and you can skim it off the tank when you're producing it in large-scale reactors. And if you've engineered the chemistry properly inside the microbe, you can drive away on the fuel that you've produced. And in fact, a company I started, Amyris, is producing fuels in Brazil from sugarcane, and those fuels are fueling buses in Sao Paulo and Rio, and they've fueled flights, Lufthansa flights and Azul flights between Miami and Sao Paulo. Now, one of the interesting features of these fuels is that when it gets very cold high up in the altitude or in cold countries, they'll freeze in the tank. And so you want to have a few branches in the fuel. So in my laboratory, we've engineered the chemistry inside microbes so that we can put those branches in just the right locations. There's a lot of genes that you have to introduce and change in the metabolic pathway. But when you do that, you can introduce branches that make the fuel just the right quality so that it won't freeze in the winter. And we get mixtures of these fuels. They're not pure fuels, but they're very similar to the fuels that we now get from diesel, from petroleum, namely diesel and jet fuel. Now, I'd like to talk about these fuels on the right there. There's two fuels there, farnesene and bisabolane. Farnesene is a fuel that Amyris, the company I started, has pioneered, and that's the fuel that's in buses in Sao Paulo and Rio. And bisabolane is a fuel that our research institute, the Joint Bioenergy Institute, has pioneered. Both of these fuels have extremely low melt points, which means they can be used high in the altitude as jet fuels. They can also be used as diesels. We produce these fuels using a separate set of metabolic pathways, a set of metabolic pathways that in you and me is responsible for cholesterol production. Now, if you divert the cholesterol production in an organism like yeast, you can divert it to produce these fuels, and you can produce gasoline-like fuels, like isopentanol, which is a great gasoline replacement. You can produce monoterpenes, which are great jet fuel replacements. And by the way, they smell really nice because a lot of these are constituents of perfumes and colognes. And we can produce sesquiterpenes, longer, higher molecular weight hydrocarbons that are great diesel replacements. Now, the way we do this is we engineer the chemistry inside cells, and then we go into plants and we look for the genes that will produce these fuel molecules. This one fuel that I talked about, bisabolane, has almost identical fuel properties to number 2 diesel, so that when you can substitute it directly as a drop-in fuel. We get the genes from plants. In this case, we got genes from grand fir, shown there up on the right. And when you take these genes out of the plant, you put them into a yeast. You can redirect the metabolism from producing cholesterol-like molecules into producing these diesels. Now, I want to talk just a bit about all the other products we get from petroleum, because I think we not only can we produce fuels, but we can also produce all of the other things that we would normally get from petroleum. And I've got a diagram up here of a barrel of oil to remind you how many products we get from oil. If you take a typical barrel of oil, 80 to 85% of that barrel goes into producing fuels, gasoline, diesel, and jet fuel. The other 15% of that barrel goes into producing all of the products we use on a day-to-day basis, from the carpet on the floor to the material and the fabric on the chairs, the plastic on the chairs, the paint on the wall, the paint on the ceiling. All of these products come from petroleum, and we have the ability to replace them with exact replacements, but make them from things like sugar. Now, the value in doing that can be incredible. The value of that 15% of a barrel of oil is roughly equivalent to the value of that 80 to 85% that goes into producing fuel. So in the US, fuel market is about a $1 trillion market, and that 15 to 20% that goes into those other products is about a $1 trillion market. So we've been now engineering microbes to produce a lot of the same products that we would normally get from petroleum, but yet get them from sugar, and the list is extensive. And I just want to, in the last few minutes, talk about how we've engineered the chemistry inside microbes to produce some of these valuable products. So I show up here a lot of the molecules that form the basis for carpet fibers, for fabrics, for paints. And if we could tap in and produce these molecules, we could replace the source that would normally come from petroleum. Now, I've talked about 2 metabolic pathways to produce fuels, the fatty acid pathway that produces the lipid membrane around cells, and the isoprenoid pathway that in you and me produces cholesterol. There's another pathway that's been widely used for producing our antibiotics, and it has very diverse chemistry, the kind of chemistry that we'd want to use to produce some of these other products. These molecules are produced on very large protein complexes inside cells, and those protein complexes stitch together the molecules that are important antibiotics for us to use. You can refactor these proteins and capture all of the chemistry in them and put them together in new ways that nature had never imagined before. one of the first things we went after are polyesters. Polyesters are widely produced from petroleum, and you could produce a variety of polyesters just by engineering the chemistry inside microbes to do it. So we recrafted these synthases that normally would produce antibiotics like lipomycin, put them together in new ways, and found new proteins that would produce polyester-like molecules. And the variety of chemistries that we can capture here is unprecedented. You can't get chemistry like this using petroleum or traditional catalysts that are now used. We wanted to change out some of the chemistry in these molecules, and you can do this simply by changing the proteins themselves. You change the genetic sequence that encodes the protein, and when you do that, you can then swap out the chemistry that protein would normally encode and put new chemistry in it. In doing so, then, we can produce a whole new set of molecules now that don't have a methyl group in this case, and make polyesters that have entirely different properties. Finally, I want to leave you with a set of molecules known as ketones. These are very good solvents. They're also particularly good fuels. If we could produce these molecules, then we could replace a very large sector of the chemicals industry. So we began to craft proteins that we'd put inside microbes to produce these molecules. We took a very similar synthase that we had built for producing the polyesters, and we knocked out a chemistry in it that would allow it to produce these ketones when you just add a little heat, because the additional carbon dioxide comes off when you heat them up. And we can produce now a variety of methyl and ethyl ketones that can directly substitute for those that we would get from petroleum. Finally, I want to leave you with a molecule that you all have experience with. It's called the Dybbuk acid, and it's the constituent of nylon, and it's all around you. It's in the carpet and the floor and the fabrics on the chairs. This molecule comes exclusively now from petroleum, but there are chances and ways that we can get this from sugars. And in fact, we've engineered these synthases to produce these exact molecules that we would normally get from sugar, but now get them, that we'd normally get from petroleum, but now get them from sugar. You place the genes inside a microbe, a yeast, and that organism then produces a molecule like a Dybbuk acid. So what I've shown you today is that we have the ability, using biology, to replace petroleum directly, not just molecules that are kind of like the molecules that we find in gasoline, diesel, and jet fuel, not a little bit like the molecules that we find that we're using in our fabrics, in all kinds of materials, but exactly the same molecules. And we can do this by engineering the biology. This has been brought about by a revolution in the area of synthetic biology, and I think over the next few years we're going to see more and more possibilities for replacing chemicals that we would normally get from petroleum and wean us off petroleum as a feedstock. This work was performed at the Joint Bioenergy Institute in Emeryville, California, and it was funded by the U.S. Department of Energy. I would again like to thank the organizers of this conference for inviting me and you for your time and attention.